Yeah, perfect. Okay, so thanks. First, I would like to obviously thank the organizers for having me here. And it's a great workshop. I love that we have been having like both very high-level talks, which are amazingly insightful, and some more technical ones. As part of the French team, I guess I'm going to be on the technical side of things, and I couldn't thank Peter enough for like his introduction, because actually what I'm going to present is very inspired by work of his team. That is one of like the biggest chain of influence in discussing the links between compression and privacy. Is what I'm going to talk about. And I mean, obviously, what we do is kind of a tiny building blocks in that direction of trying to have efficient federated algorithms that include some kind of privacy guarantees or other constraints. So this, I should start by saying this is based on work with Mahmoud, who is a PhD track student in my team, and Remy, who is postdoc, both at École Polytechnique, so my bad, and CT Lee, who is at Chinese University of Hong Kong. And obviously, I thank them a lot for this collaboration, so it was super nice to work with them. So I'm going to skip the slides on all the details, but actually I'm not going to need any of the notations, but obviously we are working in that federated learning framework in which we have an average of n functions that we would like to optimize. And basically we don't need too much of the technicalities here. We have seen that graph several times. The starting point of most of our research is we want to keep the data locally, then we need to exchange with some central entity. And if we do that, the simplest thing to do would be distributed SGD. That's great. The problem is that then we communicate a crazy amount of information, which is problematic both from the privacy side, because for communicating that much is going to leak a lot of information, and from the communication side, because communicating very large dimensional updates, a very large number of updates times, with a very large number of clients is not possible. So how we tackle that? We tackle that in two ways. We tackle that by communicating only a fraction of times. That's called local iterations. Or we could tackle that by communicating a fraction of weights. That's called quantization or projection, let's say. Low precision updates, that's called quantization, or with a fraction of workers, that's called subsampling. And so basically the good thing is that the last three here, the communicating with fraction of workers, fraction of the weights, or low precision updates can all be framed into one framework. It's called compression. The other one is called local iterations, like say, for example, federated averaging that Peter just talked about. And basically these two things are extremely connected in how they behave. I'm not going to talk too much about that. I'm just going to briefly mention that we are interested in compression because it enables to tackle those three aspects, like fraction of the workers, fraction of the weights, or fraction or low precision updates. And the field has been extremely active in that. I'm just going to try to summarize 6 years of research, going far beyond my own, including some from people in the room. Edward, so several people have worked on that. And basically what people end up doing is say, I'm going to put an assumption that encompasses all those three compressors. So let's say it's unbiased, maybe, oops. That's, maybe you can switch back to full screen, or I don't know if I need to do that myself. Yeah, that's okay. So maybe we do something which says that all those compressions can be unbiased and have a bounded variance, and then we do stochastic gradient descent with those analyses, and things go well, or we do contractive operations. We ensure that, let's say, if I only pick the largest coordinate, I'm going to be closer, closer to the initial vector than the scale of the initial vector. So that's all great. And basically, I would say that there are two main takeaways in that for people that don't know this literature. The first one is that there is a trade-off between compression, how much I compress, and heterogeneity, very much like there's a trade-off between heterogeneity and local iterations, and we have similar algorithms to what Pranit proposed with scaffold, where you actually have to control and throw some kind of control variance to limit the impact of heterogeneity. So this was one line of work. And the second line of work, again, this is really community work, including some of my own, but not majority, is feedback loops, is that when you do compression, you do observe the gradient before compression and the compressed version to transmit. So if I transmit to Pranit a compressed version of my gradient, I can remember the difference, and afterwards I can keep that difference and propagate that back. So these are like two of the fundamental ideas that influence the community, and now we've tried to build upon that. And obviously this is connected also to what Peter mentioned at the end, that we can introduce noise that is correlated over several iterations, and I think there are like still a couple of interesting directions in that field. Okay, so what comes next? What I'm going to talk about in this talk is different things. I'm going to want to try to say that we have to go beyond that kind of worst case assumptions on compression operators where we put all of them in the same bag. Because actually, they are, like, if you try it, it actually doesn't behave the same the same as well for two compression that satisfy the same variance upper bound. So we have to work on that. Obviously, one I don't think I will have time to talk about. The second one, which is like trying to just show how different compression operators result in different convergence rates in what we do best, which is linear regression, so high-dimensional linear regression, and trying to see what exactly the rate is and how actually the, let's say, the regularity of the compression influences. So in one word, when you do quantization, you actually have that the compression of x and y, which are very close to each other, is much further than x and y, so on average. So this is something which is of interest. And what I'm going to talk about today is trying to do compression operators that produce a specific error. So why do we do that? We do that because, for example, we may be interested in producing a Gaussian error. And if I'm able to do a compression of x, which is exactly x plus a Gaussian noise, then maybe I can have some applications almost for free. So for example, let's say I want to generate DP noise, which is Gaussian noise, and I'm just able to compress my gradient, and it results in the gradient plus the noise. Then in some sense, I get the compression from free given a particular DP. And that's basically, I think, the most important application. The two other applications we could think of, and then there are many other ones, is Langevin dynamics. So for example, Alain presented a paper yesterday in which when you do federated Langevin, you end up, if you want to do compression, compressing your gradients. And afterwards, you add some noise, which is the Langevin noise, which is, again, a Gaussian. And you could just do that, again, for free. I mean, if you know that you are going to add Gaussian noise, you can get the compression for free. The constraints are a bit different because here you don't actually care that the noise would be not revealed to anyone. We're going to see it's a bit harder in the DP case. And the third one is randomized smoothing. So, I mean, say I have my own model, I'm the central server, I compress it before passing it to Mike. And that means that Mike receives a model which is my model plus a Gaussian noise in that case. And it means that when I'm doing the gradient descent or stochastic gradient descent, I have something like that, update WT plus 1, which is WT minus the gradient of f at the random points. And this is known as randomized smoothing. And if we have density on the noise CT here, the convergence rates are typically, I mean, easier, or at least we get smoothing on a function. So non-smooth function, this is actually the expected gradient of the smooth function with a smoothing kernel, which is with respect to the noise C. Okay, so there are several applications to have in mind. And these are the main motivations. Great. So I'm going to try to show you how we can do that. And actually, there's one key idea. Okay, so first, more related work on DP. I said I need to give all the credits. So first, the high-level intuition is that DP and compression are clearly allies. If I compress drastically, I mean I say nothing, I'm extremely DP, right? I mean, I don't provide any information. So we clearly go in the same direction. I say that like, the first line of work is the one by Peter, and I think, I mean, obviously he's the expert in the room on the topic, but what's my understanding of Peter's work is that we try to see what utility we can achieve with epsilon delta dp, and then we create a compression operator that does not degrade that accuracy. And we try to find, okay, he's nodding in the right direction, that's good news. And we try to see that we can have an optimal complexity not to degrade the convergence rate. And then there is the second line of work, which is very important, which is trying to do quantization, which means we are going to work on discrete sets, but instead of compressing on, let's say, 0 and 1, I'm going to discretize on all possible values of z, and prove DP on that. It's the line of work by mostly people in Meta. Okay, and our approach is here focusing on what we call subtractive dithering, which is going to enable us to get specific noise. And as you can see, it's not a very complicated approach, but there are some things to take out of it. So we're going to focus on like producing a special noise. In fact, any unimodal noise is possible. We can do Gaussian, Laplace, anything. But I'm mostly going to talk about Gaussian because it's easiest to think about and the one that has the clearest applications. And okay, we're going to get DP with respect to an external observer, if we have a trusted server, or we're going to get DP, we're going to get secure aggregation with respect to the server, or homomorphic encryption. Great, so let's move to the technique. So that's the one slide I want you to focus about. How do we get noise that has a distribution? And the key for that is, sharing a seed for randomness generation. So the classical and most classical quantization technique is dithering. We take a vector x, and I transfer x to either 1 or 0 with probability x, which means that this has a distribution which is a binary of x, and the worst case error would be 1/4, the average case error if x is uniform is 1/6, and all is good for me. But now this is a discrete error, obviously, b of x. I either have an error of 1 minus x or x. Now what we're going to do is subtractive dithering is take the same x, we're going to first add some noise, U1, uniform noise between -1/2 and 1/2. So this is representing now my distribution in green. Try to create a color scale. And instead of doing quantization, now what we're going to do is project to the nearest neighbor. Okay, so it actually corresponds to projecting all the points right from this 1/2 line to 1, and all the points left to 0. And now I've done that, okay, I can resplit my noise into the blue part and the red part. And what I'm going to do is to transmit that 0 and 1, which is the encoded vector, and then subtract the noise. So I mean to be able to access this uniform noise on both the sender and the receiver, meaning that I generate them simultaneously. And so if now I subtract this noise in red, which was going from -1/2 to -0.2, say, to 0, it means that I'm adding 0.2 to 0.5. Okay, so you see that it reverses, obviously, the order. And if I do that to the second part, then obviously I recover that I get exactly x plus minus 0.5 uniformly. Okay, so this is what subtractive dithering is. It exists since the 50s, in fact. I mean, it was applied first in signal processing as anything, ask Eric. And the good news is that we get uniform noise with average error and maximal error of 1/12. So, okay, and you see I've tried my best to align the graphs to the small screens. So I spent part of my night on that, so I just wanted to point that out. It's very important for me. I'm happy that it worked. Okay, so now what do we aim for doing? I mean, formally we need to define a framework, and what we're going to define is a framework we call IANQ, meaning we want to achieve additive independent noise quantization. So meaning that whatever the input is, x1 to xn, we want that the output of our framework minus the input is just a noise q, which is sampled independently from x and y. And so again, as I've said, we're going to use a shared randomness S, and we sample this shared randomness simultaneously on the sender and the receiver. We encode x depending on S, and we decode the encoded version depending on S. We call M the message, okay? E is the encoder, D is the decoder, M is the message, which is always going to be on a limited precision set. And subtractive dithering is just like exactly what I've described. For any input, you sample a uniform noise between 0 and 1, and you take M, which is the flow of x plus u. This is the same thing as taking x plus 0.5 to minus 0.5 and taking the nearest neighbor. It's just like easier to rewrite. We decode by taking M minus u, and then we get exactly what I've said before. And obviously, I can do that. I can also do that with a multiplicative factor of W, and then I get a uniform noise between minus W over 2 to W of 2. And just multiply everything by W. So now how can we create Gaussian noise? I mean, basically, we're going to say that the Gaussian noise is just a mixture of uniform noises, and I'm going to first sample uniformly one length according to the distribution of the lengths of those uniforms to get the Gaussian noise. And that's something I can generate simultaneously on the sender and the receiver. So I'm generating, let's say, that FD, which is basically follows the distribution of that particular length. So, okay, I don't want to get too much into mathematical notations, but basically, I look at the distribution of the length horizontally of that uniform with respect to points, sampled according to a Gaussian noise. And if I do the mixture of my uniform noise, I exactly get the Gaussian noise. So, okay, this is called the layered quantizer. And the problem is that typically the length of the codebook, when I have very small parts here, the length of the codebook tends to explode. Okay, and this scheme was proposed by a paper by Mahmoud and CT earlier, a year ago. And so when the length explodes, because here to get this very small noise, I need to divide by D, which is very small, and divided by D very small makes my support very large. So you can fix that, in fact, by doing what's called shifted quantizer, and I'm missing a picture, unfortunately, so I won't explain it too much, but what you do, in fact, is to revert 1/2 the negative part of a Gaussian, to flip it, and when you flip it, it makes actually the length of any band positive. Sorry for the missing picture. And then you can ensure that the code size is uniformly bounded, so you have good news. So then we do theory, because we like to do a bit of theory. Obviously, this is our goal in life. So we show that basically for that, you can get both lower bounds on what you could achieve in terms of entropy, which corresponds to the minimal length of the code that you could achieve, which is the entropy of M, your signal, a message given your shared randomness, obviously, and you have basically nearly matching upper bound and lower bound, so I won't get too much into the details, but you feel that you're not doing something too bad. Okay, that's just verifies the upper bounds. So now what's our problem? That's the last thing I want to convince you about, is that when we do that in an aggregated framework, basically we don't get DP with respect to the server, at least. I mean, the server could aggregate everything and transmit that, and we have purely noise. But otherwise, the server receives our shared randomness, or sees the shared randomness. So it can subtract the shared randomness and recover our message or information on our message, which is just like the quantization of our X plus noise. So in order to get a stronger guarantee, what we want to do is to be able to average all the messages before decoding. And this is what we called, it's called homomorphic case. I want the decoder, oops, again, sorry, my bad for that. I want the decoder and the encoder to, the decoder and the average to commute. So that I can first aggregate my n messages and then only pass that to the central server, and maybe I can do some extra steps in that, and then I decode the average. And if I do that, I'm very happy. But can I do that? The problem is that if we just look at what we have done before, and I think I'm nearly out of time, so I'm going to be quick. If we look at what we've done before, basically we're sampling a length uniformly. If we do that on all clients, we get that each decoded message is going to be xi plus a Gaussian noise. Obviously, we can average those, and the average of the messages would be exactly my target plus Gaussian noise. But clearly, I don't commute, and the reason why I don't commute is that I have this di scaling factor here, and basically di is different for everyone, so I cannot average the messages mi and subtract the average of that, because di is not constant. So I need to, in some sense, fix that in order to be able to aggregate before decoding. I want to have a fixed constant here. That's exactly what you can do. So you say, instead, I'm going to have a shared randomness t, which is this t, and we all select a uniform noise. We do the same scheme, but with fixed t for all clients. Now we all have the same scaling factor, and because we all have the same scaling factor, we can aggregate and then decode instead of decoding individually. But now the noise that we get is clearly not Gaussian, because each of these variables is conditioned to t is a uniform between minus t over 2 and t over 2. And so the average is not Gaussian conditioned to t, it's actually what is called an Irwin-Hall distribution. It's a sum of uniforms. And that's at first a problem, because conditionally to t, I don't get the Gaussian distribution that I want, but now I can just do a mixture on t again. So I need to decompose a Gaussian of any given parameter sigma squared as a combination of Irwin-Halls that corresponds as the sum of n uniform noises between minus t and t, for t being a random variable. And so that's just what we want. We want exactly that. The sum of these decoded messages that are those Irwin-Halls is basically Q. And just, finding such a decomposition is a very simple rejection technique, and then we get, ultimately, that we get exactly what we want, which is our A, and Q aggregated homomorphic mechanism. And I think, okay, we can, again, do theory on that. I'm not going to do that. And basically, I just summarize the theory is, again, trying to provide control on the number of bits you have to transmit. And then I can summarize the different schemes you could get, basically starting from direct quantizer, the shifted one, in which I reduce the maximal number of bits. Then Irwin-Hall. Irwin-Hall is being neither DP nor Gaussian noise. So neither actually something you can do Rini DP on, at least. Then aggregate Gaussian, and then you can do subsampling on that in order to match as closely as possible what Peter has done. And yeah, that's the conclusion. We're trying to find a way to generate a specific noise distribution. I think there are still directions to explore on that. Personally, I hope that we can do something that improves optimization when we choose the noise distribution, but this is up for debate. Whether there's something more than just the squared noise, the squared moment of the noise that matters. And we have controlled communication cost and applications that are already mentioned. Thank you very much.
Thanks so much. I see you. So thanks a lot for focusing on the construction and the technique, but I think the slide that you skipped is actually important. So how does that improve on the other schemes?
The ones you have, for example?
Let's see.
Yeah, in some sense, it's just saying that if my understanding is correct again, what you show is, say I want to do epsilon delta dp, can I add, can I do some kind of compression that doesn't decrease accuracy? And what we say is that, say you want to do epsilon delta dp, what is the budget you can do that for free? Now, if your budget is bigger than that, communication budget, then I can reduce it. If your budget is lower than that, I can do epsilon delta dp with better parameters epsilon delta than you did. So in some sense, either your budget was larger than the one I had, and I can reduce it and do the same epsilon delta, or it was smaller than the one you had, and I can improve your guarantee. So it's just saying that we can have something that is tight. And then we can do it on coordinates if we have the trusted server, a bit like you did. But okay, there are a few things we could discuss. I think that goes into the deal. Okay, so and I had one image on that, but unfortunately it's very far in the slides, so I need to rush in the bonus slides, which is basically say that, okay, basically if we compare to your scheme, we don't gain much. We gain something like a factor of 2, typically on the variance of the gradient. And we gain that little when we are in the regime in which we do subsampling. You know, if we're in the regime where D is small and we don't do subsampling, then we gain much more. We gain something like a factor on 4 to 8, I think even sometimes a bit like 16 on the number of bits. So that depends on the regimes. In the regimes where we really want to be in n epsilon squared or n squared epsilon squared and not D, we gain a factor of 2. Otherwise, we can gain something a bit bigger, like 16.
While Alexei is setting up his laptop, maybe we can take one final question if there's anything. Otherwise, let's thank Aymeric again.
Thank you.